Well, to continue with the discussions of the last class, what did we do? We first found out the graphical representations of the PVT behavior, and after the graphical representations of the PVT behavior, then we came to the mathematical representations of PVT behavior, and then we discussed, we found out that there were different equations of states, the cubic equation, the virial equations of state, and we started discussing the cubic equations of state. And there we found out that the cubic equations of state, they have got some very strong advantages. The first advantage is that we can, as we had found out in the last class, the first advantage was since it is cubic in volume, it is capable of predicting not only the behavior in the gaseous phase, but also in the two phase region as well as in the liquid region. That was number 1. And then we also found out the drawback in this particular case, that in the two phase region we found out that it was not capable of predicting the isotherm, the nature of the isotherm. It showed a continuous curve. We had discussed all these things. Well, the next thing, and I had also shown you the list of the different cubic equations which have come up, and for the present class I had already mentioned that these 3 equations, they are the most important equations which we will be dealing with. As we see in all the 3 equations, there are 2 empirical constants which are characteristics of the particular nature of the gas, and when we are dealing with mixture, naturally it is a function or it is a mixture property which can be expressed in terms of the pure component properties, as we shall see later. Now, for each and every gas, if you are taking up, say for example, the van der Waals equation, we need to find out A, B for everything. So, we are just increasing the number of known parameters that we need for when we are going to deal with PVT behavior of gases. That is not a very desirable situation. So, therefore, in order to reduce the number of unknowns, usually what is attempted is to express the empirical constants in any cubic equation of state in terms of the critical constants, because as we have already seen, the critical constants, they are true constants characterizing any particular pure substance. So, therefore, there has always been an attempt to predict the empirical constants in any cubic equation of state in terms of the critical constants, and it is very easy to do it. Say for instance, if you take up the van der Waals equation of state, this is the equation, right. So, therefore, we have one equation as P equals to RT by V minus B minus A by V square. We can have another equation if you differentiate it. This can be one equation, this can be the other equation. So, from these 3 equations, we should be in a position to find out A and B, right. And these are at t equals to Tc, sorry. So, from this we can find out A, B, but a more straightforward technique of doing this is that if we remember that at V equals to Vc, T equals to Tc and P equals to Pc. So, what we can do? We can just write down the equation in the cubic state, it is V cube minus 3 V square Vc plus 3 V Vc square minus Vc cube equals to 0. From where did it come? We know V minus, if V equals to Vc, V minus Vc equals to 0. So, V minus Vc whole cube will be equal to 0. I have just expanded this, right. And then I have compared this with the original van der Waals equation written in the cubic volume. What is it? This is going to be V cube minus B plus RT by P V square plus A by P V minus A B by P equals to 0, right. And here we know that at the critical point, what do we have? We have Tc, we have Pc, we have Pc, we have Pc here, right. So, therefore, this equation has been written down as a cubic in volume at the condition of V equals to Vc. This has been written down in the cubic of volume at the condition of V equals to Vc. So, therefore, both these equations should be identical, or in other words, the constants should correspond to, the constants should be equal in both the equations. So, if we compare the constants, what do we get? By comparing the constants, we get, in fact, we get 3 equations by comparing the constants. If you see, we get 3 particular equations, and we will find that 2 of the equations, they are same. So, we get 3 Vc equals to B plus RTC by Pc, this is one. And then the next equation which we get is 3 Vc square, which is equals to A by Pc, and Vc cube, this is equals to AB by Pc. From these two equations immediately what comes out? From these two equations immediately we get B equals to Vc by 3, right, we get this. And if we substitute this particular equation in this term, then what do we get? We get A equals to 3 Vc square into Pc, right. So, we have expressed A and B in terms of critical constants, but both of them contain Vc. As again I repeat the same thing, that temperature and pressure, they can be much easily measured, more accurately measured, more easily regulated. So, naturally we would like, and it is much more easily evaluated, as we have seen Tc and Pc is much easily evaluated as compared to Vc, for which usually we resort to the disappearing meniscus experiment, which we had discussed in the last class. So, therefore, we would like to express A and B in terms of Tc Pc instead of Vc. So, for that, what do? We take help of this particular equation, and we know that in this equation we get 9 B is equals to B plus RTC by Pc, right. 3 Vc from there we get, which gives us B equals to RTC by 8 Pc, fine. And in the same way we can also say that A equals to 3 Vc square Pc we have found out. Again we can substitute Vc equals to B by Vc equals to 3 B, we can substitute it here, and finally from there what do we get? We get A equals to 27 B square Pc, which gives us as 27 Pc RTC by 8 Pc whole square, right. So, therefore, A is obtained as 27 RTC whole square by 64 Pc, fine. So, therefore, we could express both of them in terms of Tc and Pc. Now, this particular exercise I have shown to you for the van der Waals equation of state. You are advised to take up a similar exercise for both the Redlich-Kwong equation of state as well as for the Peng-Robinson equation of state, and you will find that for both the cases, proceeding in the similar manner, we would be in a position to find out the empirical constants of the equation in terms of Tc and Pc. So, therefore, this has enabled us to reduce the number of constants that we require in order to characterize the properties of any particular gas. But more important than this exercise brings up a very interesting results. Let us see what is the result that this exercise brings up. Again we start from the basic equation. This is the basic equation, right. If we again start from the basic equation and we substitute A and B in terms of what we have obtained A and B. If we substitute them in terms of this equation and this equation, what do you expect we are going to get? From here, what do we get? For the first equation, substituting A and B, we get P plus 3 PCVC square by V square into V minus Vc by 3. This is nothing but equal to RT. Agreed. Now, suppose I divide both the sides with PCVC, or I multiply with 1 by PCVC. Suppose I do this, then what do I get? Just observe the equation very carefully. I get P by PC plus 3 Vc by V whole square into V by Vc minus 1/3 equals to RT by PCVC. This RT can also be written down as RT by TC PCVC by TC. Can I not write it down in this particular way? Just observe this part. What does this show? P by PC is nothing but it is known as the reduced pressure. So, therefore, this can be, when I rearrange this can be written down as PR plus 3 by VR square VR minus 1/3 equals to 8 TR by 3. Do you understand the importance of the equation that we have obtained? Here what have we done? We had started, just note, with the van der Waals equation. It had two constants characterizing the gas. So, this equation should be having different forms for each and every gas that we take. From here, for where have we arrived at? This particular equation, which has no constants characterizing a gas. It almost appears like the ideal gas equation PV equals to RT, where it is the same equation for any particular gas that we use. So, therefore, we find that starting from the basic van der Waals equation, starting from this particular equation, we find that we have arrived at a particular equation which is independent of any particular constant, right. And so, therefore, this particular equation is expected to be same for all the gases, or in other words, we can say that two gases, when they are having the same PR and TR, should have the same VR, number one. Number two, suppose we try to calculate the Z from here. From here, if we calculate Z, what is Z equals to? Again starting from the basic van der Waals equation, this is nothing but Z can be expressed in this particular form, and from here we find out again, if we substitute A and B, what is the final form that we get? From here, the final form which we get is VR by VR minus 1/3 minus 9 by 8 VR TR. So, therefore, what do we find? That Z also at the same conditions of, see what have we got? VR, it is a function of TR PR. Z, it is a function of, apparently it appears it is a function of TR VR. So, therefore, Z is also, since VR is a function of TR PR, Z is also a function of TR PR. So, therefore, we find that in this particular way, if we start substituting different properties, which we will be doing later, we find that all of them are unique functions of TR and PR. So, what does this mean? This means that the gases, when they are at the same conditions of TR PR, they exhibit the same reduced properties, or rather they have the same reduced values for the different properties. Now, this particular characteristic of the gas, which has come out from this can be obtained from any cubic equation of state, and this particular property of the gas it is known as it is given by the law of corresponding states. This is known as the law of corresponding states, that all gases under the same reduced conditions exhibit all same type of properties. And from here we can also find out one more thing. What is Zc equals to? Can you tell me? Zc is equals to, suppose you calculate Zc from here, we find that this is equal to Pc Vc by RTc. You try to find it out from the basic van der Waals equation, and we find that Zc for all gases, it reduces to a unique value which I have mentioned here, it is 0.375 as obtained from van der Waals equation. It is, sorry, we find that from the van der Waals equations, if we are trying to do, we find that more or less we find that Z is obtained as a unique value, which is 0.375 for van der Waals equations, 0.333 for Redlich-Kwong equation, 0.3 from the Peng-Robinson equation of state. And the way I have obtained this particular equation, which is written here, the way I have obtained this particular equation and I have derived this equation, it can be done in an identical fashion for other cubic equations of states. Naturally, the more complex the equation is, what happens, the more complex the reduced version will also be, and the more difficult the deduction is going to be. But with any cubic equation of state, we find that we can finally express the behavior of any gas using the reduced cubic equation of state in terms of the reduced parameters and those equations that do not have any constants characterizing the gas, and for each particular equation of state we find that they predict a unique value of the critical compressibility factor. The values which we have got are different for different equations, but each equation shows that ZC should be having a unique value provided the gases correspond to the this is known as the 2 parameter law of corresponding states. For example, if I give you a very specific example, say carbon dioxide and nitrogen, right. For these two gases, I can very well tell you that just like all the gases, for these two gases, say suppose at a constant Tr and say at Vr equals to 20, Tr equals to 1.5, both the gases they should have a Pr which is equals to 0.196, right, because they obey the law of corresponding states. For carbon dioxide, I know PCO2 equals to 14.3 atmospheres, 1.9 liters per mole, and TCCO2 actually, this should be PCVC and TCCO2, this is 456 Kelvin. For nitrogen also we find the PC is going to be 72.87 atmospheres, TC is going to be 304.14 Kelvin, Vc is going to be 0.094 liters per mole, right. So, therefore, from here, and we know that at say Vr equals to 20, Tr equals to 1.5, they should have the same reduced pressure, and this particular state it corresponds to, say if you calculate it out, you will find that this corresponds to a pressure of nitrogen as 6.58 atmospheres, 6.58 atmospheres, volume of nitrogen equals to 1.8 liters per mole, temperature of nitrogen 189 Kelvin, and in this particular case for the PCO2 this corresponds to, I am sorry, these were the corresponding states, I am extremely sorry, the PC, these are the states which correspond to this, and the PCVC for these are 72.877 atmospheres, TC is equals to 304.14 Kelvin, Vc equals to 0.094 liters per mole, right. And for nitrogen the see, these are the two corresponding states. I am extremely sorry. For nitrogen this is going to be 33.55. For nitrogen this is going to be 33.55 atmospheres. Vc is going to be 0.09 liters per mole, and Tc is going to be 126.2 kelvins, right. And so, therefore, the corresponding states are for corresponding this is PCVC for CO2, this is PCVC for nitrogen, and from there we find that carbon dioxide at 14.3 atmospheres, 1 liters per mole, 456 Kelvin, that corresponds to nitrogen at 6.58 atmospheres, 1.8 liters per mole and 189 Kelvin. So, from here what do we find? We find that for any particular gas, if we know the critical constants, then for that gas at any particular condition we should be able to find out the reduced parameters. We know that even an unknown gas will have for the same reduced parameters, say for the same reduced Tr and Pr will have all the other reduced properties the same. So, therefore, what we can do from here, we can find out the critical constants for any particular unknown gas from the known critical constants of a known gas. So, therefore, this shows that we have started from an approximate equation, the cubic equation, but the cubic equations, what have they shown us? They show us that the properties of all gases are same if they are compared at same conditions relative to the critical point, or if they are compared under the same reduced parameters. And this is a very powerful law. This is given, this particular law of corresponding states is exhibited by all the cubic equations of states that we have. The functional forms are of course different. So, from there we got an idea that for all gases there should be a relationship as Z is a function of Tr Pr. This is given by all cubic equations of state. But mind it, the functional form which is given, that is different, but definitely that such a relationship exists, this is evident from all cubic equations of state, and the functional form, for that we need to resort to experiments. So, from resorting to experiments we found that this is indeed a characteristic which is shown by different particular gases. And for all the gases, what do we find? We find that indeed for all the gases, we find that it is really true that Z, it has a unique relationship with Pr and Tr, and for wide number of gases, these particular graphs have been plotted. These graphs are available in any book of thermodynamics. And we find that from these particular graphs, they have been drawn for two different conditions of PR. One is for a lower PR, the other is for a higher PR. We find from these two equations, indeed this has been, they have been tried for a number of gases, and indeed Z is a unique function of PR with Tr as parameters, and they hold very good for non-polar gases, and for similar molecules of the gases, these are extremely applicable. Okay, more or less we find that this particular law, this law of corresponding states, it appears to fail near saturation curve. This is something important, it appears to fail near the saturation curve and also at the critical point. Apart from these two places, more or less we find that the predictions, they are within plus minus 5% for non-polar and slightly polar gases. More or less we find that other than these two conditions, they can predict, the law of corresponding states holds within plus minus 5% for non-polar and slightly polar gases. Remember, deviation is large for highly polar gases. So, therefore, we find that this is a very powerful tool we have, and people have often tried to use this when in absence of any other additional data. And it is also very important to note that cubic equations, they are approximate in nature, but the law of corresponding states holds for a large number of gases, usually for most of the conditions. Now, before I end the class, I would just like to place before you why this happens. Why do gases obey the law of corresponding states? The reason is, if we take up any temperature scale, even the Kelvin scale that has been made by us, the gas does not know, or the numerical value of the temperature which we assign to the gas is not known to the gas, but the gas knows its critical conditions. It knows how far removed it is from the critical conditions. So, relative to the critical condition, it behaves identically. All gases behave in the same way at the critical point, right. So, when it is equally removed from the critical point, it behaves identically, and that is the reason why each and every gas, it obeys the law of corresponding states. Now, there is one thing I would like to mention, that if suppose we can make a finding which is totally leak proof, absolutely accurate, then there is no need of any additional research. That never happens. Whenever we find something, we find that there are some fallacies, some limitations which have to be overcome. So, therefore, additional research goes on in this particular way. In this case also, it was the similar thing. People found out that law of corresponding states is very powerful, it can be applicable under most of the conditions except the conditions which I have mentioned, and we find that more or less the deviations, it is less than 5% for extremely non-polar molecules, etc., but otherwise it can extend to 10 to 20%, 10 to 15% as well. So, naturally people wanted better predictions. So, for better predictions, what was needed? They thought that the deviation from the law of corresponding states, it primarily arises because of the intermolecular interactions between the molecules. So, therefore, if a third parameter can be incorporated which would account for these intermolecular attractions, then or intermolecular interactions, then possibly a better law of corresponding states can be proposed. Accordingly, people started thinking about what can be the third parameter to be incorporated in the law of corresponding states, and two schools have come up with two particular third parameter. For one particular school, it was Z, it is a function of TR, PR and ZC. For the other particular school, which is a much more popular thing, apart from TR, PR, they have introduced something known as the acentric parameter. So, in the next class what we do, we go for discussing the 3 parameter law of corresponding states, and we find that the 3 parameter law is more accurate than the 2 parameter law of corresponding states. So, we go for the 3 parameter law when we find that the 2 parameter law is not very accurate. We continue in the next class.